All right, Unit 14. Only 2 more units left. Okay, so we start our electrochemistry unit with a little review of balancing redox equations using the half reaction method. What did redox stand for? Reduction is re. Doesn't matter what I do, I'm always going to mess it up. Redox. Ox is oxidation. Okay, we got that right. Oxidation is what's happening to electrons. Losing electrons. So what's going on with charge and oxidation? If we lose electrons, charge goes up. All right. Reduction is gaining electrons. Rig. It's the rig and oil rig. And if we gain electrons, what happens to charge? Charge goes down. Okay, so let's go do some practice balancing. You already know how to do this. Looking at this particular equation, there are 2 things changing oxidation state. What are those? Manganese and very good. Y'all are awesome. So we'll go ahead and start with the manganese. You're going to pull out of the equation anything that holds manganese in it. And now we're going to balance the half reaction using the steps that were listed on the previous page. The first step is to balance everything but H's and O's. That's done. Now we're going to balance O's using water. How many on what side? How many? 4 on the right. Then we're going to balance H's using H plus. How many what side? 8 on the left. So now we're going to balance charge. We can balance charge by adding electrons once to one side only. On the left, our overall charge is a +7. On the right, our overall charge is a +2. How many electrons to what side? 5 on the left. Done with the first half reaction. Now the other element you guys mentioned to me was carbon. Carbon is changing oxidation state, so we're going to take anything out of the equation that contains the carbon. Balance everything but H's and O's. We need to balance those carbons. This is people tend to skip these when they see that first step. They tend to skip it because they want to go straight to those oxygens. Got to watch that. But now our oxygens balance, so we don't have to add water. To balance H, we add 2 H pluses. Now I have an overall charge of a 0 on the left and a +2 on the right. What do I get rid of that charge? How do I do it? 2 electrons. So in order to add these up, I have to have a common factor of electrons lost and gained. So what's my common factor? 10. So I want to multiply the top by 2 and the bottom by 5. I'm going to go through and change this to 10, 16, 2, 2, and 8. And then I'm going to change the bottom to 5, 10, 10, and 10. So when I add these up, I can always cancel something out, which is what? Electrons. Now I can also do what I say called cleaning house. Is there anything else that we have on both sides? Yeah, notice we have 10 H pluses here and 16 H pluses there. I'm going to take away as much as I can from one side, totally getting rid of it on one side, leaving with some on the other. So how many can I get rid of? 10. If I get rid of these 10, it leaves me with 6 here. All right, is there anything else? No, it looks good to me. So I'm going to have 6 H pluses plus 2 permanganate ions. What's the name of this acid? Oxalic acid, good. Plus 2 Mn plus 2s plus 8 waters plus 10 CO2s. Now this particular problem says we're in an acidified solution. Are we? Yes, we are, because I have H pluses here, so that means I am done. And that's balanced. Okay, let's move on to the next one. Now we're going to have to be a little bit more careful here because look what it says. Basic. You're going to do the exact same steps you've already done. We're just going to tack on an additional step at the end. What 2 elements are changing charge? Iron and bromine. So what do you want to do first? Okay, we'll do iron. Fe plus 2. Balance everything but H's and O's, done. Balance O's, done. Balance H's, done. Balance charge, 1 on the right. All right, now we're going to take the bromine out. anything holding bromine. Balance everything but H's and O's. Done. Balance O's using water. How many what side? 3 on the right. Balance H using H pluses. How many what side? 6 on the left. Then we're going to balance charge. I have an overall of a +5 on the left and a -1 on the right. So 6 minus here. Okay. Now in order to add these up, I need a common factor of 6. Oh, look. 6, 6, 6. Awesome. Once again, Satan has entered the building. All right. So when we add these up, is there anything I can clean? House? No, well, I got to get rid of electrons, but other than that, I'm going to get rid of those. And so I end up with 6 iron 2s plus 6 H pluses plus BrO3 minus gives us 6 iron 3s plus Br minus plus 3 waters. Now, am I done? No, I'm not, because it says basic solution. Currently, I'm acidified. Who remembers what I need to do? Add enough OHs to tie up those H pluses. So how many am I going to add? I'm going to add 6 OH minuses. I just put parentheses because if I don't, people think it says 60 H minuses. It's 6 OH minuses. What does that make here? Water. So I end up making 6 waters there. Making 6 waters is going to require a little house cleaning now. What do? I'm going to get rid of these 3, leaving me with 3 here. All right, so there's my final answer. 6 iron 2s plus 3 waters plus a bromate ion gives us 6 iron 3s plus a bromide ion plus 6 hydroxide ions. So y'all, that's back in your heads? Remember how to do it? The only advice to you is if you come across this in your homework, sometimes they give you the problems in the Zoom doll text where you have spectator ions in it. And so it'll be like ferric nitrate and sodium. And you're like, how do I do this? Make it net ionic before you even try to start balancing it. Once it's net ionic, it's easy. Okay, moving on. Now we're going to start. This is not physics. This is chemistry. Y'all are going to be, earlier they're like, oh, this is physics. No, it's not. You happen to cover it in physics as well. And so we're looking at volts. We're looking at electromotive force. You're going to be looking at some batteries in a few days. We're going to be talking about what chemicals we need to use to make batteries of certain voltages. So electromotive force is abbreviated EMF, and we see it as E cell. Okay? We measure this in the unit of volts. You already know what the unit of volt is. What is a volt? No, not coulomb per second. Joule per coulomb. That's an amp. We're going to cover that in a little bit. Joules per coulomb. So it's a unit of, it's energy per unit of charge. Okay. And in our world, we look at a Faraday, which is 1 mole of electrons. We don't look at the individual electron like they do in physics. We look at a gaggle, a mole of electrons, and they come in the mole. So when we are measuring this, they're going to, let me show you on this next page. They're talking about E naught being the standard voltage. You're going to look at it. We're going to look at a table in a second of reduction potentials that is under standard conditions. Our standard conditions in our batteries, it's going to be solutions in the battery all have to be 1 molar. We're at 1 ATM and 298 K. Okay? Why do we use E-cell? What's important about E-cell? E-cell is going to give us a way to determine spontaneity. If we have a battery that is not spontaneous, what do we call it? Dead. Exactly. It's a dead battery. That was good. You caught on. I didn't have to give it to you. Good job, Julian. And his hair is flat today, so he doesn't look stressed. You've had a good Monday, huh? I can tell you're reasonably calm. It's good. So if the E is positive, it's going to be a spontaneous reaction. If the E is negative, it's non-spontaneous. We want our batteries to have a positive E, or they're pretty much useless. What were the 2 other ways to determine spontaneity that we've talked about? Not in this unit. Delta G. Delta G is negative. We have a spontaneous reaction. And one more way? delta S of the universe. If that's positive, we also have spontaneity. So those are so far the different ways we can tell if something's spontaneous. So how does this relate to what we're doing in chemistry? I want you to skip to the chart. I turned it sideways on the, I apologize to those of you at home, you'll have to turn your head left. Good luck with that. Maybe I can turn this around. It'll be kind of hidden, but whoa, here it is. Yeah, the green thing, because I turned it weird, usually the green thing's on the right, but oh, there it goes. Okay. Yay. Go technology. So this is a table of standard reduction potentials. If you notice, every single one of these half reactions are reduction half reactions. To make a full reaction, we need a reduction and an oxidation. Okay? So we'll ultimately be combining two of these together. One is going to stay reduction, and what are we going to do to the other one? We're going to flip it and change the sign of the voltage. Okay? Now, how do we know which one to flip and not flip? Well, that's based on the value of these numbers. Do you see how they're in numerical order? Okay? The more positive the number, the more positive the reduction potential, the more apt it is to be reduced. So we are going to flip the less positive number. We're going to flip the smaller number on the number line. Okay? That's the one that's oxidized. We'll leave the reduction one alone. This is a really good table. It's better than pretty much any in your book. I found this many years ago. And the reduction potential on the AP test is a lot smaller than this. So usually just put in the ones you need, kind of mixed in with some you don't. So you know it's not going to be as cumbersome trying to look through. But this one covers everything you'll ever need. So you can use this as your main resource. What's important for you to realize, this is going from negative to positive. There are some teachers out there who will say, oh, if it's higher on the chart or if it's lower on the chart, you choose that one. Well, you can't look at it that way because some tables will list it from positive to negative. You have to look at the value of the number. The higher the reduction potential, the more apt it is to be reduced. So don't be like, oh, it's higher on the chart. That's how you actually might have learned it in Chem 1. It's the more positive the reduction potential, the more apt it is to be reduced. We never know what's going to show up on the AP, which way they're going to put those numbers. So let's go back and do some problem solving. All right. Which of the following species is the strongest oxidizing agent? Let's talk about the word agent. Does anybody remember about agents? We had something reduced, something was oxidized. What was the agent? Is that a coconut? Why do you have a coconut on your desk? Well, happy birthday with your coconut. What the heck? Okay, sorry, we're going to get back on. That just kind of threw me off there. Wow. Tomorrow, what's tomorrow? Pineapple or a mango? Okay, what is the, oh, it's an actual coconut? So when you said you could have some, you weren't kidding. Okay, we'll do that after the lecture. I don't think people at home need to be listening. Did you already drink the coconut milk? How did you open that? Why am I carrying on a discussion with you about the coconut? I don't care. All right. Which of the following species is the strongest oxidizing agent? The oxidizing agent contains the element what? Reduced. And that's the thing. Remember, the agent is opposite. So we are looking for the element that's going to be most apt to be reduced. In terms of electromotive force or voltage, that translates to what kind of number? We're looking for the most apt to be reduced. What number are we looking for? The highest, the largest number. The largest number. Okay. I have to say, in my 14 years of teaching, I've never had a student without a coconut. It's a first. I like firsts. That's good. Now that's a challenge. Y'all are going to be coming now with all this random stuff. A machete. A Tonka truck. Okay. So what we're going to have to do is you guys are going to have to help me, and you're going to flip back and forth. and find the values of the reduction half reactions for these things being reduced. Okay, so go ahead and start looking and holler them out when you get them. Any order, whatever you see first. I'm going to pause because it looks like they're a little slow. At home, they're a little slow, so not y'all at home. In here, they're slow, so those of you at home will have to wait. Hold on. Pause. Okay, so we got 1.51 for our voltage for our permanganate ion. Our bromine 2 was 1.065, and our calcium plus 2 is our negative 2.84. So which one is our best oxidizing agent, meaning the one that's most apt to be reduced? This dude right here. The MnO4 is our strongest oxidizing agent. Okay, next, will aluminum displace copper 2 from an aqueous solution? The question is asking, is this spontaneous? That's what the question wants to know. Will it happen means, is it spontaneous? So what does that mean? Is he, I just told you, is he not plus or not? If it's plus, it's spontaneous. So we have to calculate the overall E of the reaction. Well, why do we care? Who cares if this is spontaneous? This is a really, really good thing for me as a chemistry teacher. Let's say I have an aluminum spoon I want to use to mix my copper 2 ions with to get the solution mixed up, or an aluminum stir rod or something. Not that they make those, but, or if I want to store my copper 2 in an aluminum can. Do we want it to react? No. So this would be a reasonable calculation for me to do to figure this out. These are net ionic equations. So we have solid aluminum. Will it displace the copper 2? Meaning, will it boot copper 2 out? So just do AP style. What does this make? Al plus 3 and Cu. Take it to 0. So in order to find the E, we need our half reaction. So I'll start with copper, not for any particular reason, but I'm going to go copper 2 to 0. And to balance this, H's and O's are all balanced. All I need to do is add 2 electrons. This is a reduction half reaction, so go ahead and find me the voltage of that as is on the table, because this is a reduction table. 0.340 volts. Good. Now aluminum, on the other hand, aluminum going to aluminum plus 3 will add 3 electrons to the right. This is actually oxidation. So you're not going to find this, but you will find the reverse. So tell me what number you got for the reverse value. Negative 1.674. You got 6? But because it's flipped, right, this is as a reduction, but this is oxidation, so we're going to change the sign. So when we do this, we end up getting about 2.01 volts. We don't need the actual value, but what does this tell you? Positive, so it's spontaneous. Okay, now let's go ahead and get an overall balanced equation. If I were to add this up, what would I do? Common factor of 6. So this one times 3, this one times 2. So I'm going to do it all in one swoop. I'm going to go Cu plus 2 times 3, and then plus 2 times aluminum gives you 3 Cus plus 2 times aluminum. Is anybody, I'm surprised someone hasn't hollered at me about something yet. Is there something I should have done or didn't do, or is this good? Someone's suggesting that I multiply the voltage by the 3 or the 2. It's not like thermo, we don't. Okay, let me just explain why. We know that this is a unit of, the volt is energy per unit of charge. So Jasmina's not here today, so I'm going to use her. Let's say I wanted to push Jasmina down the stairs. Okay, so my energy is my push, and she's my charge. So I'm going to push per unit of charge Jasmina down the stairs. That's a demo push per Jasmina, right? By definition, that's what this voltage is, a push per Jasmina. If we all of a sudden clone 3 of me and 3 of Jasmina, and we had 3 pushes per 3 Jasminas, would my push per Jasmina change? No, and by definition, that's what I'm doing. A volt is a joule per unit of charge, okay? So do not multiply. I'm just in the habit of always doing this math first before I ever balance this. You will have to come in on lots of problems, especially when we get into the Nernst equation, and balance these because you'll need these coefficients in addition to the voltage. I'm just in the habit now of doing this first, then doing that, so I'm not tempted to multiply. Okay, I'm going to turn the recording off, and I want all of you on your own to do number 5. The setup is identical, it's just different chemicals. And I want you to write your half reactions, your voltage, and your overall balanced equation. Okay, so in doing this problem, you should have come out with spontaneous. You have the 2 half reactions, and you have what their voltages are. Did y'all get this answer? Now, one thing I failed, so this is spontaneous as well. So I forgot to answer the question in number 4. Should I store my copper 2 in the aluminum? No, it's going to react. Okay, that was kind of the point of that problem, and I forgot to bring it up. Okay, next page. Yeah, we don't need to do B. Literally, this is exactly the same thing. Let's just plow through this. They're just asking it a little differently. Here, they're wanting the value of E. We didn't have to find the value of E in the last problem because they were just wanting to know if it was spontaneous. And here it says, and determine which of the following reactions will occur in the forward direction. What does that mean? Exactly, if they're spontaneous or not. If they're spontaneous in the forward direction, they're going to have an E positive, E not positive. Okay, so I'm going to do this super fast. Ready? Go. PB goes to PB plus 2 plus 2 electrons. Cl2 goes to Cl minus. Got to balance that, so I got to put 2 electrons here. All right, let's look these up. This I haven't done yet, so you're going to help me find these. This is where we slow down. PB plus 2 to 0, I got as negative 0.125. So this is positive 0.125. Has anyone found Cl2 yet? Since that's reduction, we're going to leave it alone, 1.3. And yeah, my examples have been great. They've all been positive. Things in the world aren't always going to be spontaneous. So what does our E naught come out to be? Someone with a calculator? 1.483? 1.483 volts. So is this spontaneous in the forward direction? Yeah, yes, holla. Is that how you spell holla? Yeah? Are you sure? You brought a coconut to school, and you're questioning how to spell holla. I was told to capitalize it, but holla. All right, so tomorrow, be ready. We're going to draw voltaic cells tomorrow, batteries, electron flow, all that jazz. It's good times.